Now I'm going to go down to demonstrating my object-oriented change detection algorithm based on. Sorry. Now I'm going to get on. Now this is going to be a demonstration of my change detection algorithm in action. You'll see. It follows the pseudocode that you observed in my PowerPoint presentation. It's most of it. That is. Take note of the section titles. They'll guide you through how things progress. So first part, which I've already run, is I input the video files and I read the frames. And then the next step is for me to collect the data banks or images from the frames. So I'll show you each set. There's the running horses, the dancing guys. You saw these image sets in the PowerPoint presentation anyway. All right, now this is where things get interesting. Now the next step is creating a map of the image objects utilizing the SLIC algorithm. So that's why the section here is titled Image Segmentation Apply Simple Linear Additive Clustering SLIC Algorithm to each set of images. Remember what I said? Each image uses the same map. So a map of image objects. So that just for reference, that's the image object map, and those the regions of the image objects, and here it is overlaid on one set of images, the running horses. Image set 2. Image set 3. Image set 4. Set 5. And that's the last one. Now this is where next up is the fourth step, the third, or the other two parts of, at least are the final two parts of the algorithm pseudocode. So that involves calculating the correlation coefficients and finding the total number of unchanged image objects and the total number of changed image objects based on the threshold range. So first you calculate the correlation coefficients, and then you use the threshold range to determine how many image objects are changed and how many are unchanged. So I'll demonstrate it with one set for the first set of images to start. As you know, happening pretty fast. As you see, this is what you see before you is the path, is the image object, at least the set of image objects between both images that are being compared. So as you see, it's happening for that. Figure 6 is image, is the first image input image at time n, and in figure 7 is the image at time n+1. So each so remember each of these image objects represents a region of correlation, which is represented as one image object in the end for the results. Referred to as one image object in the results. Now if we look at the results, these are the two image results to take note of. That's the total number of image objects that calculated were changed for 16. It calculated that both 16 regions of comparison were changed and 33 were unchanged. You saw I showed all the results in the video, in the presentation, that is, video presentation. I'll do this. I'll do it for the next image set. I mean, why not? And the result, 34 changed image objects and 15 unchanged image objects. Six changed image objects and 13 unchanged image objects. This is image set at 4. Changed 31 changed objects and 18 unchanged objects. Finally, image set 5. It's harder to note. I know it's harder to notice which image object is being. The set of image objects is being analyzed because this image was, to remember, was taken at nighttime. so the contrast is lower. So is the brightness. There are 34 changed objects and 15 unchanged image objects. One thing I forgot to add was when I tested the algorithm out, it got a little confused with image objects that I believe that obviously don't change, but it might, for some reason, it might have thought they would change or not. So in the algorithm, I just marked I took note of the only the regions where they're of interest. These image objects where that are just black are outside the pixels of interest, and so I just by default I marked them as unchanged. The algorithm didn't calculate if they were changed or unchanged. And the same thing, I did the same thing for all 5 image sets. And that's that. That's my demonstration. The mathematics are all the same as you observed in the presentation.